Bismillahirrahmanirrahim. Assalamu alaikum everyone. I am Maha Sharazi, your computer teacher, and this is your assignment number 7 of grade 7. There are some guidelines which you need to follow before starting your assignment. Attempt the assignment on a separate sheet. Draw the margin lines of about ½ inch on both sides of the sheet. Write your name, RCN, grade, section, campus, assignment number and subject, and then start the written assignment. Maintain a file of assignment to be submitted when school reopens, and give at least 30 minutes per day to the assignment so you can easily finish it on time. So today we are starting the chapter Binary Systems and Hexadecimal, which is present on page number 12 of your photocopied notes. So we will go through from page 12 to 19 binary system and hexadecimal chapter and solve the activities. Okay, so first of all, the introduction. As you progress through this book, you will begin to realize how complex computer systems really are, and by the time you reach chapter number 12, you should have a better understanding of the fundamentals behind computers themselves and the software that controls them. However, no matter how complex the system, the basic building block in all computers is the binary number systems, and this system is chosen since it consists of ones and zeros only. Since computers contain millions and millions of tiny switches which must be in the off and off position, and this leads itself logically the binary system. A switch in the on position can be represented by 1, and a switch in the off position can be represented by 0. So now we'll talk about the binary system. We are all familiar with the denary, the base 10 number system, which counts in the multiples of 10. So this gives us the well-known headings of unit, tens, hundreds, thousands, and so on. Okay, so whenever we say 10 raised to power 0, it means 1. 10 raised to power 1 means 10, 10 raised to power 2 means 100, 10 raised to power 3 means 1000, and so on. So the binary system is based on the number 2, thus only the two values 0 and 1 can be used in this system to represent each digit. And using the same method as denary, this gives the headings 2 raised to power 0, 2 raised to power 1, and 2 raised to power 2, and so on. The typical headings for binary numbers with 8 digits would be, we always read it from right to left, 1, 2, 4, 8. Basically they are multiples of each other. 2 2s are 4, 4 2s are 8, 8 2s are 16, 16 2s are 32, 32 2s are 64, and 64 2s are 128. Okay, so our typical binary number would be 11101110. Now the next topic is converting from binary to denary. So it is really straightforward to change a binary number into a denary number, and each time as 1 appears in a column, the column value is added to the total. We are going to watch some videos regarding to the respective topics, and in this manner you will be easily understand all these topics.
In this video we're going to look at converting a binary number such as 01101100, and this binary number we're going to try and convert it into a denary number such as 32 or 64. I haven't even checked to see what this is going to convert into yet, so let's see if we can figure it out together. Now to convert this 8-bit binary number into denary, we're going to first of all need to draw a little table to help us out. Now the table is easy to remember because it always starts at 1, and the only step you need to remember is to double as we go up. So double 1 is 2, double 2 is 4, double 4 is 8, double 8 is 16, double 16 is 32, and double 32 is 64, and double 64 is 128. That is the bits that you need to understand. You need to remember that there's 8 columns we're going to require because we've got 8 digits here. Now we're going to go and write in underneath each of these columns the digits in order that they fit. Although this might seem fairly trivial, and some people try and squeeze the numbers on top of here, I think actually going through the process, spacing it out clearly, when you come to that crucial moment in an exam when you need to get this right, drawing the table is very helpful. So I'm just going to go and copy this across, I generally start from the right hand side. Sometimes you'll be given a number without the 8th number written on it. And in that situation you just assume any numbers to the left are zeros. So if you always draw from the right hand side, 0, 0, 1, 1, 0, 1, 1. And assuming we hadn't been given that number, we'll just put a 0 in there. So now we can see which numbers are required and which ones are not, essentially. So any zeros mean that we don't need that number, and any ones mean that we do need that number. So let's go and write out the number that we need here. So I'm going to start off with, do we need 128? Nope. Do we need 64? Yes, so I write out 64. Do we need 32? Yes, so I write out 32. Do I need 8? Yes. Notice I'm keeping my columns here because I'm going to be adding these up. Do I need the 4? Yes. Do I need anything else? No. So in fact it's just these numbers that I'm going to have to add up. Now I strongly encourage you to use whatever method your maths teacher has taught you and which one you are comfortable with. But we're just going to be adding up those numbers now. So 4 add 2 is 6, 8 add 6 is 14, add the 4 is 18. Carried my 1 because I'm using this method of addition. 6 add 3 is 9, add the 1 is 10, and I've got to the answer of 108. So now it's fair to say that the binary number 011011100 is equal to the denary number 108. Again, this one being binary and this one being denary.
Now the second is converting from denary to binary. So the reverse operation, operating from denary to binary, is slightly more complex, and there are two basic ways of doing this. The first method is trial and error, and the second method is more methodological and involves repetitive division. So just watch the video of conversion from denary to binary.
In the last video we looked at converting a binary number to a denary number. This time we're going to get a denary number, like let's say 94, and we're going to convert that into a binary number, the zeros and ones. To do this we're going to have to draw out our table just like we did the other way. So we're going to start with 1, double it, 2, double it, 4, double it, 8, double it, 16, double it, 32, double it, 64, double it, 128, and I've got the 8 columns I require. So if I want to represent 94, I need to be thinking about which of these numbers am I going to need to make up 94. Now if I used 128, I would already be over the top of 94. So I know that I'm definitely not going to need 128, so I can draw a 0 in it. Now because I know that 64 is less than 94, I know that 64 can go into the 94. So I'm going to say yes, I'm going to use this 64. Now at this point I like to keep a running total of what I'm up to. Now this sounds a bit silly at this stage because I've only got one number, so I am up to a total of 64. So I'm just going to make a note in any way you like. I'm going to do it at the bottom of this line. I keep my lines long here. I'm just going to remember at this point I was up to 64. So the next stage I need to do is, if I added on 32, would I be over the top of 94? Let's just figure that out. I'm just going to do write 32 underneath and add those two things up. 64 add 32 is 4 add 2 is 6. 6 add 3 is 9. That gets me to 96. That's above the 94, which tells me that I can't add on 32 because I'm going to be over the top of it. So I know I'm at 0 here, and I'm still only up to 64 with my number because I decided not to add on the 32. So on to the next step. Can I add on 16? Well, I can go and write 16 underneath here and see where we get to. 4 add 6 is 10, 6 add 1 is 7, add the 1, 8. That gets me up to 80, and that is under 94, so yes, I will have the 16. And that reminds me I'm up to 80, so I can just put 80 underneath that line there. I can then see if I want to add on the 8. This is where it gets a bit easier. I can do mentally in my head that if I add on 8, I'm going to get to 88. I'll write it like this just for comfort. But I'm up to 88, which is fine, so I did need the 8. Yes, so I need to put a 1 in there to say yes, do count the 8. And now I need to remember that I'm up to 88. Can I add 4 onto 88? Well, 88 add 4, that's going to get me up to 92. That's fine because I need to go to 94, so 1, yes, I do need that 4. I'm now up to 92. If I added on 2, actually that's going to get me right up to my 94. So add on my 2, that gets me up to my 94, the magic number I was aiming for, so I do want the 2. That reminds me I'm up to 94. Do I want to add 1 onto 94? No, that's going to put me over the top, so I could just put a 0 there. What this has told me is that if I could say that the number 94 in denary is equal to 0, 1, 0, 1, 1, 1, 1, 0 in binary.
The next topic is measurement of the size of computer memories. A binary digit is commonly referred to as bit. 8-bit are usually referred to as a byte, and the byte is the smallest unit of memory in a computer. Some computers use larger bytes, but they are always multiples of 8. For example, 16-bit system, 32-bit system. So 1 byte of memory wouldn't allow you to store very much information. Therefore, memory size is measured in the following multiples. 1 kilobyte, number of bits 2 raised to power 10, and equivalent denary value is 1024 bytes. In the same manner, 1 megabyte, 1 gigabyte, 1 terabyte and 1 petabyte is also represented in denary manner. Now in 1.4 they are giving us an example of using the binary digits. This section gives an example of use of binary system. We will introduce the idea of computer registers. This subject is covered in more depth in chapter 4. A register is a group of bits. It is often depicted as this. In the figure 1.2, they are showing a register which is 100101111. When computers or microprocessors are used to control devices such as robots, registers are used as a part of control system. The following example describes how registers can be used in controlling a simple device. A robot vacuum cleaner has 3 wheels, A, B and C. A rotates on a spindle to allow for the direction changes as well as forward and backward movement. B and C are fixed to revolve around their axis to provide only forward and backward movement and have an electric motor attached. As you can see in the figure that there is a wheel A that rotates in the forward and the backward direction, and it can also rotates on a spindle to allow for direction changes, and B and C are only present to give the forward and backward movement. So in figure 1.3 you can see that there is a register of 8-bit registers and which is used to control the movement of robot vacuum cleaner. So number 1 register says motor B on, second bit says motor B off, then motor C on, motor C off, B direction forwards, B direction backwards, C direction forward, C direction backwards. So if the registers contain 10101010, this means motor B is on and motor C is on, and both motors are turning to produce the forward motion. Effectively, the vacuum cleaner is moving forward. Now there is an activity, you need to solve this activity. What would be the effect if the register contained the following values? So you need to write out the effect of all these questions. The next topic is 1.5, the hexadecimal system. The hexadecimal system is very closely related to the binary system. Hexadecimal, sometimes referred to as the simply hex, is a base of 16 system and therefore need to use 16 different values to represent each digit. Because it is a system based on 16 different digits, the number 0 to 9 and the letters A to F are used to represent each hexadecimal digit. A is equals to 10, B equals to 11, C equals to 12, D equals to 13, E equals to 14 and F equals to 15. Using the same method as denary and binary, this gives the headings of 16 raised to power 0, 16 raised to power 1 and so on. The typical headings for hexadecimal number with 5 digits would be like 1, 16, 256, 4096, 65, 536. Since 60 is equals to 2 raised to power 4, this means that 4 binary digits are equivalent to each hexadecimal digit. So we are using 4 binary digit for one hexadecimal value, as it can also be shown in a table of 1.2 that the binary values has 4 bits. You see 000, there are 4 bits of a binary value. In hexadecimal value they are only represented by 1 bit, that is 0, and also it is showing in the denary value, it is also representing by the help of only 1 bit. But we can see that when it comes to the point after 9, at point 10, at position 10, it converted into A, 10 equals to A in hexadecimal value, and after that 11 equals to B, and 12 equals to C, go on till F, which is equals to 15. Now the last topic is converting from binary to hexadecimal and from hexadecimal to binary.
In this video we're going to look at converting between binary to hexadecimal, which is fairly straightforward. If we start off with a binary number, so I'm just going to say 0, 0, 1, 1 and 1, 1, 1, 0. So we've got this binary number that we'd like to convert into hexadecimal. Now, what we need to do when we're converting between binary and hexadecimal is look at each block of 4 bits as a separate hexadecimal number. So traditionally with binary we would look at this as the column headers being 1, 2, 4, 8, 16, 32, 64 and 1, 2, 8. But that's not going to work in our system to convert to hexadecimal. So instead we need to break it down into 2 component parts, and each of these works on the initial system. So we're going to say 1, 2, 4 and 8, and I'm just going to put those numbers underneath that. So we've got 0, 0, 1 and 1. We've then got these 4 digits, and again they work on the start of the table. Just draw a line to separate here. And these are 1, 1, 1 and 0. I've just copied down from above. You'll notice all I'm doing here is just changing the column headers. What we can do now is for each of these 2 different sides is we can add up what the numbers equate to. So we've got 2 and 1 here added up. Well, this is quite straightforward. I know that 2 add 1 is 3. So this side equals 3. Now believe it or not, that is our simple conversion to a hexadecimal number. That counts as a hexadecimal number, which seems awfully easy, I know. On this side, we're going to do a similar thing. We've got 8, 4, 2 and 1, so we don't need to count the 1, so 8 add 4 is 12, add the 2 is 14. Now I've got a problem here because there was no 14 in the hexadecimal system, and I always end up messing up when I try and figure out on my hands or on my fingers what is the letter representation for 14, which is why I'd always encourage you, particularly in an exam, to jot it back out, so that I know that in hexadecimal 9 is equal to 9. And I could have done this all the way up, 0, 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, 2, 3, 4, 5, 6, 7, 8, but this is the bit where I get confused, so I like to start from here. So what is 10, 11, 12, 13, now I only need to go up to 14 for this problem, because that's the number I got here. So 10 I know must be A, 11 must be B, 12 must be C, D, E, and there's my answer. Again, this isn't completely necessary if you want to do it on your fingers, but I promise you when you're panicking in the exam, you will slip up. So we don't actually want to call it 14, we want to call this E. With the 3, we can refer to this hexadecimal as 3E. So we can say the binary representation of 0, 0, 1, 1, 1, 1, 1, 0 equals 3E. And that is converting between binary to hexadecimal. 3E is normally, just to be extra clear, denoted next to each other, just like so. So now let's look at converting between a hexadecimal number and converting that to a binary number. So I could start off with, let's say I want to convert D5. And this D5 number I'm going to convert over to be hexadecimal. So, sorry, this hexadecimal number I'm going to convert across to be binary. So let's first of all just double check what the value D stands for. I'm just going to draw my little table like I did in the last video just to confirm what it will add up to. So 9 is 9, so 10 must be A, B, C, D, that must be 11, 12, 13. So I know that D is 13. So I'm just going to write underneath the D 13. And the 5 must be equal to, well, 5. Very nice and simple. Very straightforward now. All I need to do is convert each of those two numbers into two sets of 4 binary representation. So I'm going to go 1, 2, 4 and 8. 1, 2, 4 and 8. Just a little line to separate those out. Now 5, how can I represent 5? Well, we could go down the line we did before. Does 8 go into it? No. Does 4 go into it? Yes. Does 2 go into it? No, that takes me up to 6. Does 1 go into it? Yes. And that gets me to my 5. 4 add 1 is 5. How do I get to 13? Am I going to need an 8? Yes, I am. If I add on 4 to 8, that's going to get me to 12. Yep, I'll have that. If I add on a 2, oh, it's going to get me to 14, so I don't want that. And if I add on the 1, it will get me to 13. So I can safely now say that D5 is equal to 11010101. Fantastic.
Converting from binary to hexadecimal is fairly easy process, starting from the right and moving left. Split the binary number into groups of 4 bits, and if the last group has less than 4 bits, then simply fill in with zeros from the left. Take each group of 4 bits and convert it into equal hexadecimal digit using the table 1.2. Okay. So now there are different examples and some activities are also there. You need to convert the following binary numbers into hexadecimal numbers. With the help of these videos, I think and I hope so that it will be easy for you to solve all the activities which are mentioned in your assignment task. For that, you need to go from page 12 to 19 and you have to do this activity which is given in your lab task. Convert the following binary numbers into denary numbers. Okay, so inshallah see you in the next electronic class. Till then, take care of yourself and Allah Hafiz.